Okay, hello everyone. Today I'm going to talk about imbalanced large graph learning framework of FPGA logic elements packing prediction. Don't be tricked by the name. This does not improve the packing, but yeah, this aims to improve the global placement solution and its legality actually. And as you can remember from the last week's presentation of Alex, the array adjustment stage of global placers has a mechanism that adapts the demand and supply of the instances. For example, if we have more demand than the supply, we increase the cell area and that way tries to push away the instances from that tile location. And if demand is less than the supply, we decrease the cell area and try to pull the other ones into the corresponding cell area. And this terminology is highly used in routing congestion and pin density estimations as well. And here you can see an example from the simple paper. For example, here are too many overfilled pins, and we increase the cell area here to spread these illegal molecules. And packing prediction is kind of provides the resource demand estimates. For example, if we say that if we consider the packing prediction on this tile, we see that there are many unpacked elements. So their area will be adjusted, increased, and they will be spread out.
And so that was like the main focus of this paper, which is that if I could predict this cell is not going to pack where it currently is, I'm going to make it a bit bigger so things will spread away from each other, and hopefully I can resolve that congestion.
Yes.
What if, for example, that cell is in a tile that it just can't fit into?
We will increase and it will change its location, and global placement will take another iteration. Yeah.
Gotcha, interesting.
And here are, for example, some example flows that use the area adjustment that I mentioned, like the new paradigm paper, ELF-place, and the successor of a ELF-place paper, multi-electrostatic. And this multi-electrostatic paper is also written by the same group of this paper.
Of ELF-place, or this paper that you're reviewing?
I'm reviewing right now, yeah.
Gotcha.
But it's highly dependent on the ELF-place. Yeah. And like, as I mentioned, there are many ways to estimate the resource demands of a tile, for example, to get the demand and supplies of a tile. And there are two existing approaches before the GNNs. The first one is static empirical model. For example, this one is implemented in Ripple FPGA paper, and they use a pretty basic estimate. Average CLB capacity is thought to be of 12 slots and 9 flip-flops, and effective demand is the corresponding ratio of, for example, 1 lot contributing to 1/12 of CLB and 1/9 of CLB for flip-flops. And estimated CLB count is the maximum of these ratios. And each primitive assigned array is the total count over the total primitives. This is highly architecture dependent actually, but it has the advantage of being simple and lightweight. Although disadvantage ignores the actual packing feasibility because it's a highly simple term. Yeah, you just count the number of instances in a tile and decide on if this will be exceed demand or not. Yeah. And the second method is Gaussian estimation, and this is highly used in the ELF-place, new paradigm, and multi-electrostatic ones that I already showed here. And in this one, we estimate the effective area of the instances using a Gaussian smoothing function. And each instance legalization movement from the given global location to legalized location is modeled as a Gaussian distribution, and they empirically choose 5-pin window around instance using Gaussian probability. They multiply the X and Y probabilities in Gaussian distribution, and the lat areas weighted average of compatible and incompatible ones, but they also consider the control set expectations for flip-flops as well, the clock and SR signals. And the advantage of Gaussian-based estimation is it's differentiable, highly adaptable to the analytical placement flows, and captures local compatibility rules compared to the Ripple FPGA. But it's still a proxy, predicts density, not actual packing feasibility, and so prone to false positive as well. Yep.
So is it prone to false positives or false negatives, or?
False positives in terms of, for example, if we have too many successful packings, it prompts to say that you will accept, yeah.
Interesting.
And after these examples of why one wants to use GNNs to predict packing, for example, in array adjustment stage, because if the existing ones are too simplistic or too indirect and hyperpulsive arrays, and we want packability at instance level for each flip-flop and LUT, and we want to capture the structural and contextual features of the netlist. For example, we want to capture the netlist connectivity and location of the global placement as well. And yeah, we want a model that could handle the severe in-class imbalance as well. So the authors proposed a imbalanced large graph learning network.
So this one is only focused on the netlist aspect of the site, so it doesn't contain any information of the architecture itself, isn't it correct?
It does not actually, yeah. Actually, it contains the architecture using the LUT and flip-flop connections. They try to embed that one.
Yeah.
Yeah.
Well, let's say, for example, I see not the architectures that you can have in VTR. So, for example, in still we have the different modes. We can have like this, and what does it start? I mean, one 6 can be made into 2 5
Yeah. But
it fractional dots. So, for example, does it also support?
no, it's not like highly. For example, I give you this like 5 LUTs and tell me if they will be packed or unpacked.
I see.
It's like given these locations, what will be like how they will be packed, but it does not check internals of the, for example, fractable or unfractable, and it's highly costly. My idea of finding this paper interesting is that actually, like, if can we compare speculative packing to using GNNs or how they will compare? Yeah.
Thanks.
So, sorry, I just wanted to confirm what Amin just asked. So this does not take any architecture information as input for the imbalanced large graph neural networks?
They does not directly get, but the they only trained on the Xilinx FPGAs.
Oh, I see. So they trained it.
Yeah.
Okay, I see.
Yeah.
That makes sense. And then the idea is that given the training, that's how it will encode the architecture.
Yes.
I understand. That makes sense.
But yeah, the rules are actually buried into the given labels or previous ground truths. Yeah.
I guess the benefit of that is that it actually is architecture. It can be generalized to any architecture. It's just you gotta train it for every architecture you use.
Yeah. Actually, like in industry, it's highly usable, but in our VTR case, it's a bit concerning.
Yeah.
And this is the overall framework. This picture actually itself explains nearly every part of the paper, and it's a highly complicated one. I will go through the physical design, data processing, and graph learning in each. Yeah. And in physical design, they given a global placement, get the legalized solution, and get the target packing label for each instance. But here, the target packing label is being packed or unpacked, given their global placement location, because one can say that wouldn't every instance will be packed eventually. Yeah, the successful instance here means that the given location is packable. Yeah.
This was actually something that confused me by the paper. What do they mean by unpacked instances in this case?
Yeah, but for example, let's say this instance is legalized in that location. If it is in the, they have an empirical maximum margin for that one. If it's in the 5, let's say CLB slice window, we say that it's packed in its region. Yeah.
Oh, I see. So this is very tied to the algorithm.
Yeah.
Okay, that makes sense.
So if this, for example, will be legalized into these two main faraway locations, we say that it's an unpacked, it's unsuccessful. And using that idea, we generate a data set, and to get a uniform data set, we partition each graph of each design graph using Metis partitioning tool to get the 10K node for each data instance. Yeah. And the second part is data processing, which consists of 2 subparts. The first one is graph establishment. Like in GNNs, you need to have a graph which consists of the adjacency matrix and the feature embeddings as well. And let me move this a bit. And the first instinct to create the adjacency matrix is to use the netlist connectivity for using, for example, each instance. But this will create too many, to increase the matrix size too much. So they use three steps of the connections. For example, given, and they choose the neighbor region. In that given example, neighbor region, they use three types of connections. The first one is congeneric connection, which consists of the same types. For example, here we have a LUT, and we connect the same block types LUT to that current LUT. Yep. And then we go to the second one, which is correlation. This correlation one tries to capture the highly bounded netlist connectivities. For example, if a LUT output is fed directly into flip-flop, we then capture these ones with the orange connections. And after these two paths, if we have anything remaining unconnected to the others, we use a residual connections using the netlist connectivity in this case. So that way we try to keep the matrix size limited and try to capture the netlist connectivity and highly bounded connections as well.
So we see in this graph, each node is like one primitive.
Yeah.
And then for the connection in this netlist, and there's going to be three types of edges.
Yeah.
Which is determined based on the way that
Yes. Yes.
Did they mention anything about what this residual is doing? Because I found it very interesting.
Actually, like it kind of analytical placement, I guess, idea, but they didn't mention what it's doing. It's like a last sweep to eliminate any island type.
Yeah, this is something we definitely should be doing for ourselves, because I do know that if you don't, in an analytical placement flow, if you have two subgraphs that are disconnected, you actually have created a problem in your solve. It makes the circuit very unstable. And so it's actually better to add some fake connections between them just to keep things together. It's very interesting.
Yeah. It might have some similar ideas here as well. And the next part in the data processing is feature extraction. And they call their feature extraction is AFE, like attributed feature extraction. They encode element types with 6-bit code, the LUT2 to LUT6 and flip-flop. And encode location via region encoding. Instead of giving location of each primitive with floating points, for example, they partition the FPGA into slices and encode the similar neighboring ones with similar encodings. So that way they also decrease the feature size for the locations as well.
I'm sorry to keep stopping you. So because they're using the 6-bit encoding from LUT2 to LUT6 and FF, they're not considering hard blocks like DSPs, multipliers, anything like that? And
not in this paper, I guess, but in the other ones, they claim that these blocks can only hold one type there, but they don't try to legalize these ones yet. It's just for LUT and flip.
That's probably because of the data set. I think the data set doesn't, from the ISPD competitions, don't require packing for those types, but I'm not sure.
Most probably, because Place doesn't have that notion as well.
All the different ISPD people don't do this. It makes sense.
And I guess UltraScale doesn't have, of course they have the DSP and envelopes, but doesn't have the NUC or the other types.
They don't have complicated things like NUCs, that's correct.
That makes sense. So did you also mention anything about the maximum size of the graph? That can because I can make email that one of the problems with using GNNs for CADA, the GNNs not, when you make the GNN like really big, it doesn't work as well.
Yeah.
So
that's
did they mention also anything about that?
Yeah, that they mentioned about that. For example, in ISPD benchmarks, the node count can go above the 100K, for example, and they use MITIS partitioning for training and inference as well. Like they limit it to 10K nodes for each instance. And the next part is graph learning overview. Graph learning using the created features here from the location and netlist connectivity. We use these generated features, train our model, and get predictions. And this graph learning overview consists of 4 stages: the homomorphic array encoder, graph oversampling using smooth technique, structure decoder, and graph-based classifier. And I will go through each of them right now. And the first one is homomorphic array encoder. This encoding part is actually where the GNN developers made their intended differences. For example, you will see a similar structure in many GNN embeddings. Given, for example, here our objective node is P, and we call it, for example, its features are X, V, and its neighbor features are X and V. We concatenate them, and you will see that concatenated with neighbors in many GNNs. The thing they introduce here is to be aware of the homophilyness among the neighbors. They subtract their current location, current feature from the neighbor features, and add this term at the end, and multiply this with the weight matrix and pass it from the activate function to get the embeddings. Yeah, and that way they try to capture if a node, for example, will be unpacked and its neighbors will be packed, it won't be affect its highly neighbor connections. They try to emphasize these unpacked ones. And after we get the embeddings for these instances, we will do graph oversampling, because in the SPD benchmarks or mostly any global placements will have highly imbalanced data of the packed or unpacked instances, and it's reported like less than 10% of the unpacked ones. So they use smooth to generate synthetic minority embeddings, and smooth is like it's written there, synthetic minority oversampling method, which uses interpolation. For example, let's say we have 2 unpacked instances there. We start from the random one, for example, start with this one and get its neighbors. In this case, it's just one. It has just one neighbor, and then then between these 2 vectors in the vector space, we select a random point between these and try to introduce this new feature and continue until we get a balanced data set. And after the smooth operation, we get a balanced data set, and we want to, the problem on the smooth is that we change the graph structure as well here. So we need to encode that backward to the adjacency matrix. So we do a simple inner product here to get the backward in adjacency matrix. And then the augmented adjacency matrix is fed into the classifier, and we do the training on augmented ones to eliminate the imbalanced data set. And they use the graph sage classifier on augmented graph. And this classifier gives the probability of each node being classified on unclassified. And then using the argmax, we can give the classes of each instance. I may want to spend some time on that. For example, when we get the features, if we are training, we go through the encoding and decoding, since we use smooth here to generate synthetic data and then train on that. But if we are doing inferring, which is shown with the blue lines, we just use Metis to partition the graph and do classification on that one using the trained parameters. And their training consists of 2 objectives. The first one is the reconstruction loss, and the second one is the classifier loss. In the reconstruction loss, they compare the generated augmented adjacency matrix and the original adjacency matrix, and get a Hadamard product between that difference and this n function, and get the Frobenius norm of that one. And this function ensures that if we don't have a connection in the original matrix, we will have cost of 1 here. But if we will have a connection there, the cost of that one will be more than 1. So if we disturb any original connection, we penalize more these. Yeah. And the classifier loss is a basic cross entropy going over each instance and each class. And the overall optimization objective is minimizing the classifier and reconstruction loss with weighted sum. And as Amin mentioned, like GNNs are prone to many large graphs. So they use Metis to partition the graphs into 10K, nearly 10K node subgraphs, and they perform mini-batch training on these ones, on the SPD 2016 benchmarks. And this is a pretty simple algorithm actually. They get the partition of the graph and start initializing network parameters, and then using that sample mini-batch, they generate the graph, and using the adjacency matrix and the features, they get the encodings, and use smooth to get the balanced data set, and then use the inner product to decode the adjacency matrix again, and then use the classifier on it, augment the adjacency matrix and the embeddings, and get the predictions, and using the arguments again, get the labels, and then just get the updated weights using the gradient. So it's a simple gradient method here. Yeah. Sure.
Just based on the fact they have two independent loss variables, I assume one of those losses is for the encoder-decoder and the other loss is for the classifier.
Yes.
So the idea being that we're trying to train two things at the same time, an encoder-decoder network as well as a classifier.
Yes. Actually.
It's a very interesting structure, actually.
Yeah.
Normally you train an encoder-decoder, I would assume, in isolation, and then once you have a good encoder-decoder, you then train a classifier. It's a little strange, but all right.
It looks like I sound like a new student assuming that the model will learn everything.
I mean, it's possible with enough data. It's just, it makes the problem harder.
Yeah, of course. Like, the solution space increases higher.
Yeah.
And you're right, the LREC is the reconstruction and CLF is the classification loss. And for the experimental setup, the benchmark is, as I mentioned, the SPD benchmarks. The architecture is Xilinx UltraScale.
Oh, sorry, where's the inference in this?
Oh, let me go through that quickly. Yeah.
Because that was training, I assume.
Yeah, here the blue line is the inference and red line is the training one.
Oh, I see.
Actually, this, as I mentioned, this picture is highly explains nearly everything about the paper. Yeah, given a global placement, they establish the graph and extract features, and then using Metis partition the graph.
Oh, so they do the partitioning in inference as well?
Yeah.
Okay, that makes sense.
And then construct the graph and get the encoded features, and then use it in the trained classifier.
Oh, but so in inference they don't use smoked?
Yes.
Huh.
They don't.
That's interesting.
Yeah. Like
Okay.
for training, they don't want the model to be balanced on one instance, but yeah.
Okay.
So smoked is only used to increase the number of designs probably?
Yes.
Or to probably have like a better coverage in that vector space?
Yes, actually, like.
So this is why that's used for training, but for inference you don't need to use that?
Yes, yeah.
Yeah, the reason why I'm confused is that normally when you have imbalance in your data set, you would just remove the positives. So for example, if I had an 80-20 split of my positives and negatives, you would just reduce your positives so they end up being 50.
Yeah.
You don't make up fake data for the false.
That's what
I think that's a standard.
yeah, one of the main problems is also to make sure that basically all of the points in this huge vector space is also covered.
Oh, you want
Yeah.
all the points in the vector
Yes,
space?
yeah.
Okay,
Yeah.
I see what
So
you're saying.
probably that's why smoked is used.
Yeah, because they have a limited, I guess, data set, for at least for the ISPD ones. They
That makes
may not
sense.
want to lose that one as well. Yeah.
By the way, did they mention how many designs they use for training and how many?
They didn't mention it. It's a concern in my mind as well. Yeah.
ISP.
Okay.
That's probably should be one of the most important things.
Yeah, like it should be at most 20 circuits, but
I see.
they partition them into like more than 10 for each.
Yeah, okay.
I assume they use the entire data set.
Yeah, the ISPD 2016 benchmarks contained, if I remember correctly,
Yeah, fine.
20?
Yeah,
Kinda,
so I'm
yeah.
fine.
Oh, no, 12.
12.
Yeah, so I'm fine with using all 12, but I guess how did they divide between training and inference? That's my question.
Oh,
No, yeah.
like what was the test set? What was the training set? That's a good question.
Yeah. And like that's a question I have in my mind as well, and they didn't mention this.
Then we know what it is.
Yeah. Like it might be all overlapping as well. In my mind, I'm not sure.
And for those who are just like, when it comes to machine learning and AI, you should always keep your test set and your training set separate, because if you test on the same thing you trained on, it's like if you took a test 100 times to make sure you're prepared for that test, then take the same test and say you aced it.
Yeah.
It's usually a bad idea.
The only thing that comes question in my mind for that one, for example, is the metis here
Yeah.
not being unique on these ones. Yeah, but the data set is highly similar. And like, the architecture is the Xilinx Ultra Scale graphs is highly large without metis, and they did evaluation on the Vivodo using routing. Yeah, after the design. And they first compare their packing prediction accuracy with the other methods. The first one is the Gaussian method from Elfplace, and the second one is the cluster stage, which is an improvement about the cluster GCN, which is another GNNs for classification. And their predictions are pretty high compared to the other ones.
Just, what is F1 score? Is that like a race?
Yeah, it's defined as, I guess, 2 times precision times recall over precision plus recall.
Sorry,
Yeah,
Data analysis.
Yeah,
and stuff,
that-
don't worry
yeah.
about it.
Should I say 8%? Is that like, whoa, 8%? Or is that like, oh, 8%?
It's like mid-range, at 8%, I guess. Yeah.
Okay.
Oh, sorry. Yeah. Yeah, like their F1 score and area under curve is like highly improved, but we will come to the impact on the quality of results later. Yeah. And they secondly compare the feature extraction results. Like the one I mentioned, AFE is the attributed feature extraction, and they compare it with the generalizable cross-graph embeddings, GCG, which is coming from another routing estimation paper. Maybe
Maybe packing estimation?
no, they do routing congestion estimation, but
Okay.
use embeddings on the graphs as well. So they took that embeddings from, compare these.
So I'm noticing that the ISP benchmarks had 12 circuits and they are testing on 12 circuits.
Yes.
So what are they train on?
They're, I guess, training on the same data set, and
Well, you see how many also evaluate all of these LLM models. So ChatGPT is also tested on the same.
No, what are you talking about? ChatGPT uses fair and balanced data sets. I did have a question about this, because when I saw this paper, I had no idea what the right graph is saying. Is it saying that 100% false positive rate leads to 100% true positive rate for the red curve or all curves? So I was very lost on what these curves actually mean.
actually this means, for example, like the more you close to these edges, more your accuracy is high, for example.
Oh, okay.
And it gives more true positive rate and less false positive rate, which is expected. Yeah, and like they kind of signal that most of the improvements are coming from the AFE embeddings, and then EMLG is better than the cluster sage as well.
Oh, I get it. I was looking at this backwards. You have 100% true positives, therefore you have 0% false positives.
Yeah.
Okay.
And
What does the right upper corner mean?
That means that everything is correct. Wait,
But it's
No.
1-1.
Everything is positive.
yeah, wait a minute, what is going on here?
So either it's true or false, everything is positive.
But it's
What?
100% false. Oh, okay.
Right?
Oh, yeah, it's a rate.
Oh, oh, graphs. There's a paper on graphs.
yeah.
Thank you.
Is it cleared?
I think so.
Okay.
Basically, we want to be to the top left.
Yeah.
Okay.
As long as we get to the top left, yeah, it's the perfect, but yeah. And the Gaussian method gives the less area, and like in the same analogy, the area here means the area remaining there. And yeah, they claim the prediction results are pretty good, but the impact on the physical design is highly marginal. They improve, but it's a bit small. Yeah, they use the Gaussian method from Elfplace in their multi-electrostatic placer, and they use the proposed method here in their placer as well. Like they observed the wire length improved by 0.93% and slice occupation reduced by 0.90 and 0.89%.
So actually, now I have a question. So I guess I'm a little bit confused now. So I thought that this whole model would just say whether this implementation is a pack level or not. Is that correct?
Not
Then
implemented.
why do you expect this to improve the physical design on the model?
It's giving a node-based classification, not this design will be packed or not packed. For each instance, we give the packing probability, and these probabilities are applied to the array adjustment stage of the global placement.
I see.
I'm actually not surprised by these results. From analytical placement, when you make changes so high up in global placement, even if you make it like 10 times better, I found that the improvements kind of don't translate to 10x improvement later on. Not always.
7% improvement is not marginal. It's actually 0.
No, that's
No,
1%.
0.0.
That's 0.1%.
Oh, 0 point. Oh,
Yeah.
So not 0.000.
Yeah, that's marginal.
It's like 0.00.
But
Also, there is an increased, density is increased here, so it might just be that, the word.
I agree, actually. And
Might
another
be,
thing, we're missing a column. Where's runtime?
and critical path delay as well. Yeah.
Yeah, because Gaussian method was nice because it's differentiable. I can actually compute that very quickly.
Yeah.
If I could run an entire GNN and do H-metis graph partitioning and do all that sub stuff just to get these numbers, and you can do that a lot. Like they do this every iteration of global placement, I think, or at least.
Yeah.
So it's expensive.
Yeah. Like being marginal is explicable for me as well. Like you can think of the prediction as a partial legalization improvement. And its effect on the quality of results will be small, of course, but yeah, you're right. And they miss some results as well. And this paper is, I guess, accepted to IEEE transactional circuits and yeah.
Which conference was that? Was that TCAD?
Let me quickly check. 2024 April, yeah. Transit circuits and systems. It's a, I guess, general purpose one instead of focusing on FPGAs, but yeah. And I guess that's all because it was also a short paper, but I wanted to mention about the GNNs use cases in the packing prediction. Yeah, I found that interesting. Yeah. Okay.
Anyone have any questions? All right, well, thank you so much, Haydar. I really
You're
appreciate
welcome.
it. And the reporting.
It was an interesting work.